Any questions? Any comments? Yes.
In selection rules, we don't include the value of m.
The value of m?
You only think on n.
Yes, yes. So the restriction m is only this. So we said n, no restriction other than the conservation of energy. What this means is if you are going to get a photon out of an atom, you have to have the energy difference between initial and final states. So that's why I said no restriction. So the most important one is this one, delta L should be plus or minus 1, right? This has to do with photon, and delta M can be 0, plus or minus 1, and not, for example, plus or minus 2, and not plus or minus 3. So that's actually quite a bit of restriction, right? So basically, as long as you have these two rules, you can have a transition. Good. Any other questions or comments? Any suggestions? Okay, so this week we are going to start talking about the next chapter, many electron atoms. So far we had the simplest thing, right? We had the hydrogen atom, and even in the hydrogen atom, which was like a two-body problem, like a problem of proton and electron, we reduced it to a single-body problem. Like basically the proton was fixed, and only the only agent was electron. But in real life, we don't have that. In real life, move from hydrogen, like the next simplest thing is helium, and you have many more electrons. Lithium, you have many more electrons. So if you want to understand the atoms, like atomic structure in the real life, we have to think about more than one electron, and that's how we say like many electron system. But for this, we have to like think about angular momentum a little bit more. So last week, I introduced the baby version, so let's try to make this a little bit more detailed, and let's try to make sure we understand what kind of angular momentums we have to deal with in a atomic system. So let's think about, let's think about quantum angular momentum. A little bit more. So the idea was, if you remember, we could think of angular momentum to giving rise to magnetic moments. So the picture was something like that. This is my z-axis, if you want. And I have like a magnetic moment, mu, and in the opposite direction I can think about angular momentum, something like that. So this is the mu vector, this is the L vector, and I am thinking about some kind of like a precession like this. So the angular momentum precesses around some axis, and so does the magnetic moment. So then the torque on the system is mu cross B, and in vector like form I can take the cross product and I can write it like mu B. So if this angle is theta, mu B sine theta, and torque, for example, if you put like a magnetic field like this, B along Z, and mu is along this, B is along this, by right-hand rule, the torque is going to be into the page, or in this case, if I use the spherical polar coordinates, it's going to be the unit vector along the phi direction. And I require this to be equal to, by Newton's second, dl dt. But now I want to, okay, so this is the dl. I want to ask what is the change in angular momentum, right? So the length of the vector is the same at any moment, only the direction changes. Then I can think about this dl as a vector to be this, okay, this is the projection, right? I project this and it is going to be rotated in a little bit like this. So dl is going to be L. First, this is the projection sine theta, and there will be some angle d phi, and the direction is going to be phi hat. Hopefully, if you didn't know like spherical polar coordinates, this is also a good point for you to learn it. No prerequisite is required. I'm introducing everything. If you don't know, please ask. Then I can consider this d phi dt, and it is going to be what? From this equation, this is going to be dl divided by L sine theta dt, right? Or you can think about dl is going to be L sine theta d phi. So I'm just taking the magnitude, so this is on this side, and if I divide both sides with the dt, this is the equation I have. And I want to like take the magnitude of both sides. So this is going to be 1 over L sine theta. And for dl, I'm going to write this torque. This is mu b sine theta. Yeah, this is dl dt, and I think that's pretty much it, right? So this one will cancel this one, and for L, for mu, I'm going to use what we said last time. This is Q over 2m times L. So this L is going to cancel this L. At the end, I have, for electron, let's put Q is equal to E. This is E B over, do I have everything? I have Q, I have B, and I think I have M. And this is what we call omega L. This is so-called Larmor frequency. So basically what this says is like, this is kind of like a spinning top, right? And in this spinning top, if you put the spinning top in the gravitational field, angular momentum magnitude is always conserved. Of course, the real spinning top is going to slow down because of dissipation, but we don't consider that here. Only the direction changes, and the change of direction is determined by this frequency, and in this context, we call it Larmor frequency. So this is the classical picture. So quantum mechanically, we said, okay, U was coupled to external B like this, U dot B, and we said this is like additional term in the Hamiltonian. And we said, again this is, so this one is E over 2m L, and L is a vector, B is a vector. Because of dot product, B is along Z, this is going to be minus E over 2m, so this is B, and because of LZ, I'm going to write it like this M times H bar. But I can like identify the Larmor frequency here, right? This is EB over 2m, this is EB over 2m. So this is going to be H bar omega L times M. And here, okay, this maybe to distinguish this mass M from the angular momentum number M, I can put like a subscript to this M and say it is like an M, the M letter related to angular momentum. So this is ML. And ml, if you remember, can be 0, plus or minus 1, dot, 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 all the way up to plus or minus L. And what this says is like, okay, initially I had these energy eigenstates. Let me call them like E. But when I turn on the magnetic field, I'm going to have E plus this h bar omega L times ml. And basically we are saying that each line is going to split into 2L plus 1 sublines, right? So if L is equal to 0, no splitting. So if L is equal to 1, threefold splitting. If L is equal to 2, I have fivefold splitting. Let's consider an example. So example, so let's consider hydrogen n is equal to 2 to n is equal to 1 transition. I think this is, if I'm not wrong, I think this is called a Balmer line, but I'm not sure, you can check. So we have two lines. Let's say this is n is equal to 1. So this is n is equal to 1. This is n is equal to 2. And suppose I start the experiment with B is equal to 0. First, there is no magnetic field. And there is some transition. I don't know, something like that. So this is some, let's call h bar omega naught. You can calculate h bar omega naught from right from the 13.6, right, EV. We know how to calculate that. And if we look at the experiment is something like that. You have like, you are looking through an eyepiece and there's like a strip in front of you. And in front of you, what you see is just a single line. And this line corresponds to some, I don't know, 500 nanometers. If you are in the Balmer series, it's going to be a visible line. Now I want to repeat the same experiment in the presence of a magnetic field. This is now non-zero B. And I know this L is going to split into 3 because L, for n is equal to 2, L can be 1 or 0. And L is equal to 1 can split into ML is equal to plus 1 or ML is equal to minus 1. So basically this one is going to be 1 and the other one is going to be like this. So this is ML is equal to 0. So this is ML is equal to plus 1. So this is ML is equal to minus 1. And each splitting is this Larmor frequency, h bar omega L, and this is h bar omega L. And you do exactly the same experiment, and we are supposed to see not only this central line, but we also expect, for example, this line, and this line, right? All the selection rules are applied. So this is from delta, all of these lines are L is equal to 1. This is L is equal to 0. Delta L is 1 or minus 1, either way. And ML can be plus 1, 0 or 1. And there's also an energy difference. So all selection rules are good. So what I'm going to see is there's this additional, let me call it Balmer line, and it is going to split into 3 lines. And each one has some like wavelength associated with this h bar omega L. So this is all good in theory, but in real life, this is not what happens. So all this word is kind of like, you may feel like useless, but it is not. Typically, we never see this in real experiments. There are some like special cases you see this, but more often than not you don't see this. We typically never see this in real experiments.
Why don't you see?
I will come to that. That's the topic of this lecture. Let me create some tension. Hopefully I'll answer by the end of the lecture. But what we see is splitting into 4 or 6 or even more lines. Not like here, not odd numbers, but like seems like even number of lines. And more dramatic than that, there are also some spectral lines you are supposed to see no splitting at all. So some spectral lines with no splitting expected. Like for example, let me see this. You expect something like this. Say without magnetic field, but what you see, so this is what you expect, but what you find is not this, but something like, so this is the original line which is missing, but you see 2 lines. So this one is, for example, the famous one. So this is hydrogen, one of the hydrogen n is equal to 3 to n is equal to 2 transitions. We are expected to see one line at 656.3 nanometers, but we see 2 lines separated by 0.14 nanometers. So at this point, you either like say, okay, you have to see the eye doctor, and you go to your doctor, and your doctor confirms that your eyes are good. You come back and do the experiment, you still see 2 lines, and you are puzzled. And one of the people who were actually puzzled about this was Pauli. And so one of the people who was like perplexed with this result was Pauli, and your book says that somebody saw him upset, and they asked Pauli, what's wrong? And he was like, how can one be happy thinking about anomalous Zeeman effect? So these are so-called anomalous Zeeman splitting. So the one we described earlier here is normal Zeeman. So, I mean, of course, this is also like quantum mechanically interesting, but something deeper is taking place in the anomalous Zeeman splitting. So this is like a puzzle coming from spectra, but another experiment, which is like by now is like a classic experiment in the quantum realm, and it's called Stern-Gerlach experiment. And what happens is that this is kind of like a double slit experiment, but a little bit in steroids. So you have like a magnet, let's say this is south, and this is, let's say this is north, and you send your particles from here, and hopefully they have angular momentum, and as they pass through the magnetic field here, suppose, so this is, we can think about this like a magnet. Suppose this is north, this is south. And suppose there's like a force on the south. So, okay, maybe I ask you, what is the direction of force on the south pole? Is it up or down? Down. So this is going to pull down. Let me call this F of X. So this is X. And a little bit, so this is like, suppose a very tiny magnet like an electron, And a little bit later, so what is the direction of the force on the North Pole? Is it up or down? So this is going to be up, so this is F of x plus dx. And if this is like a uniform magnetic field, what can we say about f of x in compared to f of x plus dx? So no tricks, just uniform magnetic field. The problem has the symmetry you need. The magnitude of force at x, the magnitude of force on this end, and magnitude of force on this end. What is the relationship? Are they equal or unequal? They are equal, right? Because it's the same B. So this is equal, then net force is 0, so no displacement. Of course, the net torque is non-zero and it's going to rotate this object. But if you like take this apparatus and like, for example, put a screen behind like this, suppose this is your screen. So what you are going to see is like there's going to be like a single line because everything you shoot is going to go straight, and maybe there will be some broadening for the reasons that you cannot control, but typically there will be a single line. However, if I do like inhomogeneous magnetic field, so this is, let's take inhomogeneous B. What this says is like B at the location of x is different from B at the location of x plus dx. In that case, are they equal or unequal? So, right? In that case, they are going to be unequal. In that case, there will be a net force. And there will be, as a result, this net force is going to push particles up or down. And now we have to determine how they should be deflected. And to determine how they are deflected, we consider U, which is minus mu dot B. And force, as you know, is minus gradient of U. And so if this is my z direction, I am going to write it like, okay, this is mu z bz, and I can forget about vectors, and maybe I can put the vector at the end. So this is going to be mu z del bz del z along the z direction. But my mu of z is equal to minus e over 2m L z. If I plug this in, I'm going to see F is equal to minus e over 2m Lz del bz del z, and it's going to be along z direction if I'm using vectors. But for Lz, I'm going to use this ml times h bar because that's the quantum mechanical eigenvalue. And the problem has the symmetry, so I'm going to use minus e over 2m. So this is ml h bar del bz del z z bar. And this says that each ml is going to experience a different force than each, like, supposedly there's like all mLs equally divided in this initial beam. So I'm going to just separate them, as many mLs as I can. For example, yes.
First you said the direction of the forces are inverse, so the net force will be 0. Then you change your idea.
Yes. What did I do to make that unequal?
Yeah.
What is the assumption to make them unequal?
I was going to ask that.
Yeah. So did anybody get that? What is the, yes?
B is non.
Exactly. B is inhomogeneous. B in one end of the compass is unequal to B on the other end. That's required, right? As an experimentalist, you have to devise that if you want to get an interesting result from this experiment. Now we are trying to understand what interesting things comes out if we can do that. Okay? So that's the input, if you want, of the experiment. Now let's consider, as an example, consider simple system, hydrogen, H, atom. But let's say it is in L is equal to 1 state. Then ML can be plus or minus 1 and 0, right? Then there will be 3 forces, FL is equal to 1, FL is equal to 0, and FL is equal to minus 1. And at the end, if I look at this screen for this example, I'm going to have, okay, one line in the center which is undeviated, another one here, and another one here. Okay. And the amount of splitting is proportional to, for example, if I increase B gradient, the force is going to increase and the distance between these lines are going to increase. Or if I have like a bigger magnetic moment, they are also going to increase, and so on. Similarly, if we have H atom in L is equal to 0 state, then ML, right, there is no ML is 0. So how many lines do you think I should see in this case? This is the ground state of hydrogen atom, L is 0, ML can only take one value. How many forces do I have? One force. How many lines should I see? One line, right? So we expect, so here, okay, this is what we expect, but the result of the experiment is not this. What we see is we actually see 2 lines. Oh, sorry. We expect no splitting, but we see 2 lines. Just a historical note. So Stern-Gerlach was done in 1921 with silver atoms. They are like considerably more complicated. But hopefully by the end of this chapter, we are going to see how to understand this experiment, even with the silver atom. But this same experiment was repeated by, I think, Phipps and Taylor in 1927 with hydrogen. Of course, hydrogen in its ground state L is equal to 0, and they didn't find 3, and they didn't find 1, they found 2 lines. Okay, so that's the anomalous Zeeman effect. Any questions? So, after these observations, Uhlenbeck and Goldsmith proposed an intrinsic angular momentum. And what was the intrinsic angular momentum? Like so for L angular momentum, we had 2L plus 1 different values, right? But from the Stern-Gerlach experiment, we have 2 different values. So this, okay, for this new angular momentum, let's use another letter because this is a different, right? Angular momentum is angular momentum. Once you find rules, they are applicable for any case. So I just replace L with S, and they should still be, right? If they are angular momentum, they should still be the same thing. And they said, okay, if the lines are splitting into 2, this 2S plus 1 should be equal to 2, right? Clear? Which gives us S is equal to 1/2.
I didn't understand why it should be equal to 2.
Because there are two, we split the lines 2. If we split in 3, right, it would be like 3 here, and L would be 1. If we split to 0, there would be one line, S would be 0. If we split to 5, right, if this is 5, S would be what? 5/2, and so on. However many lines you see should coincide, right? This is kind of like counting. Good? So S is representing this new intrinsic angular momentum that we are trying to understand. Okay? So that's what they proposed. And this angular momentum came up to be this S is equal to 1/2. And let's remember the angular momentum as usual. L, if you look at the magnitude, was equal to h bar L plus 1. And in the case of this S, we can have S, and we are going to have h bar, but L can be only 1/2, and 1/2 plus 1 is 3/2. So this is going to be root 3 h bar over 2. Here we had LZ was equal to, now we have different kind of L, so let's put like a subscript L, and it's going to be h bar, and ML was equal to minus L all the way up to L. Now we are going to have SZ. We are just copying and pasting exactly the same solution without doing anything, and it's going to be ML h bar, but S is 1/2, then this is going to be plus or minus h bar over 2. So this is as far as you can go. And now you can try to imagine what kind of intrinsic angular momentum could this be coming from, right? We have to of course, imagine what could be happening. And maybe, okay, let's think about our classical problem again. There's like a proton, and around the proton, there's like an electron spinning, right? Right, just like this is the sun, and the Earth is spinning around the sun, and it is giving us the seasons, summer, winter. But also, like, let's extend this little sphere a little bit. This is like a big sphere, right? It can also have other degrees of freedom. Maybe it can be spinning around its own axis, which in the case of Earth is giving us days and night, right? So this one, so I'm going to put this orbital angular momentum on top of proton. That doesn't mean it belongs to proton. It still belongs to electron, but because of orbital, I'm going to put it here, and I'm going to call it L. Because now I have two things I need to distinguish. The other one, the intrinsic angular momentum or spin angular momentum, I put it here, and this is my S. However, there are many problems with this kind of classical picture. Uh-huh. So like anything rotating, right? Whether it is rotating around its own axis or it's rotating around something else, it is an angular momentum, right? And depending on the kind of motion, we have to specify, right? So now we have two kind of angular momentums. One is L, we call it orbital angular momentum, and the other one is it's spinning around its axis, and we call it spin angular momentum. And each angular momentum comes with like a magnetic moment, right? So there's like a contribution to magnetic moment from orbital and also spin.
I was trying to understand the intrinsic.
So intrinsic means like something you don't have access to, like mass, right? What is mass? You cannot go find a particle, open it, and find mass to be like some like, I don't know, like the inside of chocolate. It's like just something we don't know. It is just there. Like for example, electron charge. it's intrinsic, right? You cannot just go open and charge is like, I don't know, like some composed, right? There is no composition in the charge. Exactly like that, intrinsic angular momentum also doesn't have any composition. It is itself a property of matter. So if it was, that's actually the point I'm trying to make. If it was coming from this spinning object, it would not be intrinsic, right? It would be coming from another thing. So how can be, right? By its conflict. So now I'll try to show you that if you take this spinning object too seriously, you are going to be in very deep trouble. Let's consider like a classical charge sphere spinning, right? Let's consider classical picture. And classically, angular momentum is I times omega. And I is equal to, like suppose we don't know the shape of electron, right? As far as we know to the best, according to best precision experiments, electron is a point particle, which will be the source of the problem in a little bit. But let's suppose electron is like a sphere, and so this is moment of inertia of the object. What is the moment of inertia of like a uniform sphere? Does anybody remember? I think it's 2 over 5 m r squared, something like that. Yeah, 2 over 5 m r squared. So this is like a uniform sphere. And for omega, we can say v over r. And v is the speed at the equator. If you want, I can put like equator here. Now what we want is this L to be equal to this angular momentum we found here, right? So this is root 3. This is the magnitude of angular momentum, h bar. That's the requirement coming from quantum mechanics. And we are saying that this should be equal to I omega. And if this is the case, this is going to be 2 over 5 m r squared v equator divided by r. So this is also the radius of the uniform sphere. And okay, like I said, radius of electron is, as far as we know, is 0, but the best upper limit is like something like 10 to the minus 16 meters. So the radius of electron is definitely smaller than that. And most probably it's a point particle. But suppose we like make the worst case estimation and take this to be the radius and put it here, right? Now radius is known, right? This is r, at least that's the estimate. And m is electron mass, this is also known. H bar is fundamental constant, we know it from, for example, black body radiation and all those things. And if you do that, the speed in the equator comes out to be 10 to the 4 times speed of light. And basically what this says is like this is nonsense. So at this point, you either like say, okay, this spin, I'm not going to take it because if I look at it classically, it is nonsense. So I'll close my eyes and never think about it until somebody asks me. Or you say that, okay, this explains the experiment, but the classical picture fails. And classical picture fails all the time in this course anyways. So we have to abandon this entire classical picture and we say that, okay, this spin, whatever it is, we don't know. It is like something inside we cannot see. It is a property like mass, charge, and speed. Good?
What is the
This is speed of light. Right? Nothing can go faster than speed of light by...
Then we will find the...
No, there is no correction here. Like even if you find something like this, you know like this thing is not going to work. I mean, you can try to make this calculation in a relativistic case, which is much more difficult, right? I don't know how to do that. There may be textbooks trying to consider this, but at this level, we are saying that we'll abandon this classical description. this spin, whatever it is 100% quantum. And there's no classical analog. That's what, at least what we say. In your future career, you can read and think about what spin could be. It can be like a lifelong pursuit. But here, I don't have more to say. So, so remember the gyromagnetic ratio. Gyromagnetic ratio. So one more weird thing about spin, and I'll give you a break, is let's calculate it for spin. And it is going to be what? It is mu spin divided by L spin, and in this case, it's going to be S. And if we copy and paste what we found for like a usual angular momentum, we are going to find E over 2m. But it turns out that's 50% wrong. So there's like a so-called G factor here. So this G can be predicted, okay, like you said, for example, relativistic, right? You can do all of these, you can also do quantum mechanics relativistic, and Schrödinger equation turns into a Dirac equation, and Dirac equation predicts G to be equal to 2. So this is coming from Dirac, and exactly 2, right? 2.0000. That's right, from Dirac equation. However, exact G is not exactly 2. So there's like a difference. And you can calculate this thing and also measure it in the laboratory. And I think calculation is something like that. 1 plus alpha over 2 pi squared dot dot dot. Does anybody know what alpha is? I feel like this is like a famous number. What is its value? Yes, it's like this is a very, very tiny thing. But if you calculate, so there's so-called, if you learn QED and calculate this with so-called Feynman diagrams and up to like a third or fourth order and measure it in the lab, there is like a 13-digit agreement between G theory and G experiment. And I think Feynman was using this to demonstrate the strength and the power of the physics. Like imagine you are like measuring the distance from like California to New York, and the precision is like 1 human hair thickness, right? That's the kind of precision we are talking about. And he's saying that there's no other science that can reach to that level of precision in anywhere in the world. So what we are talking about is like quite robust, right? It's not some fluke that we are trying to fit in. So with this conclusion, now, okay, full set of quantum numbers. Now we had N, we had L. So now we have two kind of M. So let me put like ML for the first one, and now MS. So when we want to describe an electron, we have to describe all of these wave functions. And typically we say if MS is equal to plus a half, we say classically up spin. Of course, that's nonsense, now we know. If it is minus a half, we have down spin. And the wave function should be specified up to N, L, M. Of course, there will be R, theta, and phi. And there will be also some chi, let me call it chi s. And this chi s can be up with arrow or down with the arrow. Once we specify this, we specify everything about a single electron. And when you come back, we are going to start thinking about more than one electron. Okay?